Pulleys. Back in Unit 2, we looked at pulleys. Now, we're going to come back to them again. When we did pulleys back then, we said a pulley was something that was going to just change a direction of force without really doing anything else. So if I had a mass like this that I was trying to pick up, I could pull out in this direction instead of having to lift it directly. All it did was change the direction. Now that was for what we called an ideal pulley. And an ideal pulley is one that doesn't have friction. We didn't really spend a whole lot of time talking about this back then because we hadn't talked about friction. No friction, no mass. Well, we have now figured out how to handle friction in general. We haven't really done much with it rotationally, but we won't. But we know what to do with a rotating object that has mass. So, no friction we're going to stick with, no mass, that's a correction we're going to make. What a pulley does now, we have to take into account. So if we have a tabletop like this, and we stick a pulley on it, we can have a block. Oh, let's make sure it hits the top of the pulley. We can have a block like this and put a triangle mass. We can say here is a M1, here's an M2, and the pulley itself is going to get a mass. I'm going to give that a capital M, going to give that a coefficient gamma, and I'm going to give that a radius r. When we do force equations, and maybe, just for the sake of it, let's give this thing some friction too. We'll go mu kinetic. I suppose we'll let this system already be moving. So when we do this problem, we would say here is my mass 1, and I'm going to draw a free body diagram for it. Now for this is exactly the same as what it was before. We have M1G going down, we have a normal force going up, call that N1, we have a tension going to the right, and we have a friction going to the left. That should be familiar. Friction kinetic. If I stick with my axis of to the right counts as positive x, up counts as positive y. Then I have my full free body diagram. Now I look at mass 2. Mass 2 sits like this. I have M2G going down. I have tension going up. And I had to keep in mind when I did these that my axis was going to have to move. I had a y-axis like this and an x-axis like this, and then I wrapped that over so that this became my x-axis, this became my y-axis. I'm going to have to stick with that. So there's my y-axis, there's my x-axis, no surprises here. And there's my free body diagram for mass 2. And there's my free body diagram for mass 2. Now I'm going to have to look at the pulley itself because it has a mass now. So for the pulley, I'm not looking at forces, I'm looking at torques. I have a torque that pulls this way, and I have a torque that pulls this way. Now here's the thing. When I had pulleys that were massless, that were ideal, my tension was automatically equal because the pulley couldn't do anything about it. Now my tension's not equal. So there's a tension 1, there's a tension 2, which means over here I have a tension 1 and a tension 2. These are happening at a full distance of r from the axis of the pulley. I called to the right, motion to the right, my positive x direction. So I'm calling this direction of rotation my positive rotational direction. And I have a torque diagram for my pulley. Now I can start doing this. The sum of forces on mass 1 in the y direction is going to be n1 minus m1g equals m1ay. Acceleration in the y direction is going to be 0, so that tells me my normal force 1 is going to be m1g. In the x direction, I have t1 to the right minus friction to the left equals m1 times ax. I don't actually know my acceleration, so I'm going to leave that as an unknown. My friction force is mu times my normal force, so I have t1 minus mu k, and my normal force was m1g. That's why I cared about the y direction at all. Equals m1a. I have two unknowns in there, so I have to keep going. Mass 2. Sum of forces. All I've got is an x direction to work with. I have an m2g minus t2 equals m2 ax, and those ax's, those are going to be the same as each other. Because they're connected by a string. So if one accelerates, the other accelerates, they have to be at the same rate. But I now have three unknowns, t1, t2, and ax. So now I look at my pulley. For my pulley, I'm looking at a sum of torques. I have t2 causing a torque in the positive direction. And it's happening at a distance of r. So this together is my torque from force 2. And then I have t1 causing a torque in the opposite direction, also times r, is equal to, now sum of torques is equal to I times alpha. Great, but now I have another unknown, alpha. I'm going to use this same idea that this thing is going to rotate without slipping, and if that's the case, alpha is going to be a over r. That's a condition I'm really going to be able to use pretty much always in these problems, because the jump in necessary math to be able to not use that is really a jump from trig to well, differential calculus, which goes fast. Alright, I have three equations. T1 minus mu k m1g equals m1a. I have a second equation, m2g minus t2 equals m2a. And this one, when I plug all my items in, I is going to be a gamma mr squared. Alpha is going to be a over r. I'm going to get one of those to cancel. I then have t2r minus t1r equals gamma mr a, and I can cancel the remaining r, which means that equation simplifies to t2 minus t1 equals gamma m a. I have three equations with three unknowns, and I can solve this a number of different ways. The easiest way that I know of to solve this is to just add all these equations together. I'm doing that because I recognize I've got a positive t1, a negative t1, a positive t2, and a negative t2. If I add all these up, all that stuff's going to cancel. I will wait to cancel it until I've got it all in one spot. Alright, cancel where I can. I've got a positive t1 and a negative t1, negative t2, positive t2, and on this side I'm going to factor that a out. So what I get here, I'm going to pull this term first, m2g minus mu k m1g, and the right side m1 plus m2 plus gamma m times a. I'm solving for my acceleration. m2g minus mu k m1g divided by m1 plus m2 plus kind of the effective mass of the pulley. I'm already this far into an example. Usually I try and keep the example videos separate, but I mean, here we are. Let's give these some masses. We're going to give this a coefficient of kinetic friction of 0.4. Mass 2 can be 10 kilograms. Mass 1 can be, 4 kilograms. So now we know we're definitely moving in that direction. We're going to give this pulley a mass of 2 kilograms. We can give it, if it's a solid pulley, gamma is going to be a half, radius can be, doesn't matter, because it canceled out anyway. But let's plug in some values and see where this goes. m2g minus mu k times m1 g all over m1 plus m2 plus gamma times the mass of the pulley. I think I said 2 kilograms. I did. So when I plug all that in, I'm going to get something, 100. 0.4 times 4 is 1.6 times 10 is 16. 100 minus 16, that's 84 newtons on top. On the bottom, 10, 14, and 1 is 15 kilograms, and I get 5.6 meters per second squared. When I didn't have the pulley, or when the pulley didn't have mass, this term would have gone away, and I would have been left with 84 over 14, which is 6. So I would have had 6 meters per second squared I end up instead with 5.6 meters per second squared. This thing is moving a little bit slower. If I then want to go back and find the individual tensions, I can, because now I have my acceleration. So then let me see what happens when I plug numbers in. If I plug this 5.6 meters per second squared into acceleration here and here, I'm going to get tension values out. Tension 1, tension 2. Tension 1 will work out to be 38.4 newtons. And tension 2 works out to be 44 newtons. I wasn't really looking for those tensions in the first place, but I had this much, so I might as well. Now, if I would have plugged in my 6 meters per second squared, which happened from gamma here being 0, effectively, or mass here being 0, if I plug in my 6 meters per second squared to there and there, then I would get out my tension 1 would be 40 newtons, so it gets to be a little bit bigger, and my tension 2 would be 100 minus 60 equals 40 newtons, so that one goes down a little bit, and I get two tensions that match each other. Which means this problem still works based on what we had before, if we go through the whole formulation and in the end plug in m equals 0, we get the result that we had before. And that's a good consistency check.